Hi, it's Dr. J here. We are going to continue our journey of non-parallel forces and equilibrium. Today we will solve a standard drawbridge problem using the conditions required for equilibrium. A uniform beam of mass 50 kilograms and length 8 meters extends from the side of a building. A cable attaches the beam to the wall at a distance 6 meters from the wall at an angle of 50 degrees to the beam. First thing we're going to do is we're going to draw a diagram. So we have a diagram here, but we're going to need to put a little bit more detail on it. So I'm just going to draw it over here. And I'm going to put as much information as I can on here. So here is my cable, which will have a tension T. We have 50 degrees here. We also have a weight force. Oh, let me pop this 6 meters in here because that's where the cable attaches to the beam. And I'm going to make my beam a little bit shorter so it looks a bit more proportional. This is 8 meters here. Now the importance of the 8 meters is the fact that you can then tell where the weight will act through. So the weight will act through the center of the beam, which will be at 4 meters because it's a uniform beam. So let's pop that here. So this is going to be at 4 meters. And we know what the weight is because we know the mass. So the weight of that beam is equal to m times g. And we know that that is equal to 50 times by 9.8, which gives me 490 newtons. Okay, we also know that it's at 4 meters. All right, so we need to work out the tension in the cable to start off with. So there's the T there. Now, obviously, we're going to have to find that perpendicular component to the beam. So that's that perpendicular component. Now, if this is 50 degrees here, this angle over here will also be 50 degrees, making this over here T sine 50 degrees. Okay, so make sure that you put all of that on your diagram because it just makes it that little bit easier for you. We then can write our first condition for equilibrium, which is that the sum of moments clockwise is equal to the sum of moments anti-clockwise. So which is which? So let me just color code this. So if we're looking at the anti-clockwise moments, if I put my pen along the beam and I move it in the direction of the tension, we can see that that's going to give us our anti-clockwise moment. So that's the anti-clockwise moment, which is acting at 6 meters. We can also see if we've got our clockwise, that's going to be our weight force, and that's acting at the 4 meters. Okay, I just try and make it as easy as possible for myself so I don't get confused. All right, we need to write an equation down. So we need to write our RF sine theta. So let's do the clockwise. So R of the weight force, sine theta. That theta, of course, is going to be 90 degrees, so that won't be too difficult. We then have our tension. So I've got the distance of the tension times by the tension times by sine of phi. Okay, so we need to put in a pivot. The pivot is going to go where we don't know something and also not where we are trying to find something. So if that makes sense. So this is where we would put it. We don't know the force of the wall on the beam. We're going to have to find that out later, which you can see is part C. So let's put in our numbers. So the weight force is 4 meters away. It's 490 and it's sine of 90. You don't have to write that in, but I'm going to do it for completeness. So R for the tension, it is 6 meters away from the pivot. I'm looking for the tension and I've got sine of 50 degrees. So we can pop that through our calculator, but let me rearrange it for you so you can see where those numbers are coming from. And hopefully when you put that through your calculator, you end up with 426 newtons. Okay, tension doesn't have a direction. All right, now that's part A. Part B is actually quite straightforward. Calculate the force of the cable on the wall. So you've calculated the force, the tension in the cable. So the cable's pulling on the wall. So it's going to have an equal and opposite force. So therefore the force on the wall will therefore also be 426 newtons. Okay. Finally, we come to the force of the wall on the beam. Now this is something that we don't know. We're going to have to calculate it from our other condition of equilibrium, and that is that the sum of forces is equal to 0. So here what we need to do is we need to draw in another diagram showing our forces. So what forces do we have? We have our weight force, which is 490, and we also have this tension of the cable, which is 426, and this is something here that we don't know. Now, we don't know what the angles are here. The only angle we know is this one here. So that's 40 degrees between, if you go back here, 40 degrees between the cable and a perpendicular component, which would be our weight force down here. So you know that that's going to be 40 degrees. We don't know what the other angles are. I know it looks like a right triangle, but it is not actually a right triangle. So what we need to do is assume that it's not. And what we need to do is go to our formula and data sheet, and we need to use the cosine rule. So the cosine rule is this from your data sheet. So b squared plus c squared, take away 2bc times by the cos of a. So we have our two sides with the angle in between it. We're looking for a, so that's got to be a over here. And that opposite angle is the angle of 40 degrees. And then these can be either. I'm going to actually label them so I don't get confused. So I'm going to call that C and I'm going to call that B. Okay, so let's pop those numbers in. So I've got 426 squared plus 490 squared, take away 2 times 490 times by, oops, sorry, let me write that the correct way around. 426 times by 490 times by the cos of 40 degrees. And if you pop that through your calculator really, really carefully, you end up with 319 newtons. This is going to be away from the wall. Now, the other thing that we're going to have to do is we're going to have to find an angle. Which angle do you find? Try and find it in reference to either a vertical or a horizontal component in there, okay? So probably this angle here is a good one to find. So that would be angle B. So the other thing that's on your formula and constant sheet is sine A over A is equal to sine B over B. Now, I would recommend that you write these formulae down because in some instances they are worth a mark. It just depends on who your marker is, whether it's worth something, but you know, you're getting marks for nothing, so just write it down. Okay, so we then have the sine of A, which is the sine of 40 over A, which we just found out to be 319, which is equal to sine of B, which is what we're trying to find, over 426. So therefore, B is equal to the inverse sine of, and I'm going to have to cross multiply here. So I've got sine 40 times by 426 over 319. Whoa, nice calculator thing there. So I end up with 59.1 degrees from the vertical. Okay, so you can write that in a nice neat little way. So 319 by 10 to the 2 newtons away from the wall at 59.1, oops, 9.1 degrees from the vertical. Clumsy, but it gives you all the information you need. Okay, there we have it. So what we've done in this video is we have solved a drawbridge problem. Remember, it's just using exactly the same steps every time. The problem might be slightly different each time, but the method that you use stays exactly the same. Okay, thank you for listening to my video. Remember to subscribe to Dr. J's channel for the latest physics tutorial. Thank you.